Okay, we looking good?
Yes, it looks good. And okay, maybe I should introduce you again since
Refresh
some of
our
the people
memories.
join later. So Jason Efragian conducts research on neuromorphic computing at UC Santa Cruz. He has created a widely used Python library that is used to train and model a spike in neural networks. For his work, he has received several awards. My introduction is notoriously very brief. If you go to lasertalks.com, you can find a link to his website and a much longer bio. All yours, Jason.
Awesome, thank you very much. Look, I'm going to show you some of the work that I've been leading in my lab, some of the things that we've created, and truth be told, I don't fully understand it, so sorry, Feynman. But we'll do our best. We are trying. We're trying to figure out how to make these ridiculously large and parameterized AI systems and language models work a little bit better, a little bit more brain-inspired, um, and hopefully within the same power budget of what the brain is able to operate on. So hopefully a somewhat familiar uh, Google Chrome browser app. But look, if I was to ask ChatGPT, how much energy did it cost to train you? Then it's going to do everything that, I don't know, professors are phenomenally good at, and that is just talk about everything but the answer that I'm after. And to be fair, that information is not open accessed. It's not something that OpenAI are necessarily willing to release to the world. But that's okay. We do have estimates that there are a lot of consulting firms that try to reverse engineer this. But how about instead I ask chat, how much power in watts does it cost for a brain to run? And this time, fingers crossed, it'll be a little bit more succinct if I force it to be succinct. And in this case, yeah, it's very roughly got a pretty good estimate of what the brain takes to do computation. That is something on the order of 20 watts of power, the same energy it takes to light a tungsten light bulb, right? Now, if I compare that to a lot of these modern language models, it is incredibly more efficient, right? Now, some of the estimates that are out there with respect to ChatGPT and similar language models are that training cost something like on the order of millions of dollars in energy bills alone. And then you've got the salaries of all the software engineers and data curation, et cetera. But just the energy of the backpropagation training process was several millions of dollars. And that keeps increasing as the model sizes keep increasing. And historically, that has been the dominant cost of a lot of AI. But as we go into this world where what we're taking these individual foundation models and then everybody is accessing them, right? You suddenly have far more usage costs over training costs. So it's just under $1 million per day to service the many requests that ChatGPT, Cloud, et cetera, are all getting. That's honestly kind of insane, right? So with that being said, a long time ago, evolution somehow determined that the constraints of the brain meant that spikes were the most optimal way to encode information. And what are spikes? It's just that biological neurons stuck in here are somehow communicating with each other via these fluctuations of voltage, right? You get a bunch of ions moving inside, outside of your neurons, and that transfer of ions is going to cause changes in charge distribution, which means that there's a different measurable voltage, right? And we're kind of going to explore how this notion of spikes um, can be used to make AI more efficient. And truth be told, spikes all look very similar, right? Their pulse width, their amplitude, all these are very stereotypically same-ish, right? So my question is, how do we distinguish spikes? Now, it's thought that we really just care about the timing of spikes or the frequency of spikes or the difference in timing between spikes or even the sequential order of spikes, perhaps from various neurons, right? So all of these have something in common, and that is the working theory is that the brain compresses the entire world around it into something that resembles the timing of spikes, right? And that is how we're able to process and understand, etc., right? And this is very tightly related to the question that I ask and that my lab asks, and that is, how can we take advantage of this? How can we thread neuroscience into artificial intelligence? Not for the sake of it, right? But rather with the goal of making AI more sustainable. So let's dig into this a little bit deeper. I like to distill the benefits of the brain into the three S's, and we've touched on spikes. That is this idea that biological neurons interact via single bit spikes. So we've got this cartoon depiction of a spike. We've got the neuron body here. We've got the axon, which is connected to thousands of other neurons. And if I was to take an electrode and stick it into this axon, then I would be able to measure these spikes or these action potentials. But in absence of that spike, in absence of that voltage change, then what would there be? Pretty much nothing, right? A bit of noise, right? So neurons are typically very, very quiet, right? They fire at pretty low frequencies. And computational neuroscientists often like to take a step back and ignore the low-level biological details and rather look at how populations of neurons work. And so what they might say is, all right, I just care as to whether or not a spike happened. If a spike happened, I'll denote that as a 0. And if a spike happened, then that can be a 1. And if you can kind of cast this into your brain and smush spiking neurons into these ridiculously large deep learning computational artificial intelligence systems, then this is a nice way to do computation, because if I have 0, and if one of my nodes in this big graph are transmitting zeros, then 0 touching any sort of other parameter, 0 times any other number is 0. And that effectively means that I can reduce the amount of operations that I need. Right now, part of what makes deep learning so damn expensive is just this idea that modern microelectronics require a shit ton of memory accesses, right? And every time a neuron is transmitting information to other neurons in a deep learning model, well, I need to access from memory all of those weights, all of those parameters that are connected to that individual neuron, right? And that is going to lead to the motion of electrons, which is kinetic energy, which is heat, which is thermal energy, and that's going to waste power. Now, if one of my neurons is a 0, is activated as a 0, then that is theoretically quite nice, because I don't need to execute the computation. I don't need to access the memory. So that's all well and good. The second S is related to sparsity, and that is that biological neurons spend most of their time at rest setting most activations, that is, just the values that are emitting from the neurons, to 0 at any given time. And if this benefit was a computational benefit, then you could argue that this is a memory benefit, in that if I was to read this list of numbers out to you, I could say 0, 0, 0, blah, 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 7, 0, 0, blah, 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 5, but that is a ridiculously inefficient way to express this list, right? It would make a lot more sense for me to just say there's a 7 at position 10 and a 5 at position 20, right? So in that way, you're only adding to the memory required to store this list of numbers every time there is a non-zero element, right? So just to distill that, we get a benefit in computation, in reducing the amount of computation, and we get a benefit in reducing the amount of memory usage. And the brain has somehow figured this out, right? Then there's this other idea. I won't touch on this in too much detail, but this notion of static suppression, and that is the brain is only active whenever there's something worth being active in response to. And if I can give you a more tangible example, there's this thing known as an event camera that is based very loosely on how the retina behaves, right? This footage was captured by my friend Greg Cohen at the University of Western Sydney. On the left, we see a conventional camera, a few cars going by a construction site, and on the right is this event camera. Now, in sort of yellow-orange, we see pixels that are activated every time there is a sufficient increase in luminance. And then we see a blue every time there is a sufficient decrease in luminance. And otherwise, there's more or less nothing there. So you're effectively reducing the amount of data traffic that needs to be shoveled to your model. And I think that's really kind of elegant, because if data is one of the primary problems of training neural networks, then this kind of picture just shows that we could use data far more effectively. We don't need so much information compressed into our data. We can remove a lot of it and still get something useful out of it. And not just that, but if you remove everything that isn't in motion, right, then you can suddenly, maybe I'm not sure if you can see it, but you might be able to catch some little streaks of rain that are far more difficult to make out in this conventional camera. And, you know, our sensory periphery kind of really tends towards motion, right? We look at things that are actively changing, and that is what we care about. And as a result of all this, it turns out that you can slow down the speed of event cameras because all of these pixels are operating independently, right? In conventional cameras, we're used to working with frames, right? You have 25 frames per second. All of these pixels are integrating light at the same time. But with biology, our neurons are kind of, I mean, of course they're interconnected, but nothing forces them to fire together, not necessarily at least. And so this is kind of a benefit that we can take from an event camera, where if any pixel in this scene can operate independently of other pixels, it doesn't need to be contributing to a frame. It can kind of activate on its own time, and that lets you effectively slow down the footage from your event camera significantly, right? But with all that aside, that kind of tells us how these sensors attached to the brain might give us a bit of intuition on gaining engineering benefit. But what about the computation of it, right? Once you've actually collected a bunch of data, how can you use it in a way that enables you to, you know, do remarkable things that language models are capable of? We're going to start at a very basic foundational level, and we know that biological neurons communicate largely via spikes. And one of the most simplest neuron models out there is this leaky integrate and fire neuron, where you might have a set of inputs and you have spikes that are exciting, or input spikes exciting this neuron. And if this neuron is sufficiently excited, then it triggers its own output spike to everything that it's connected to. And in the absence of that, there's kind of no computation going ahead. You're removing a lot of the power or the dynamic power that your chip would, the hardware that is running these software models that would otherwise be dissipating. Now, I'm going to be very qualitative about it, but what this looks like in specifically the leaky integrate and fire neuron case is, on the top, I have the input excitation to this neuron. We get a bunch of spikes. And on the bottom could be the voltage difference between the intracellular and the extracellular medium, or just the voltage difference between the thin film membrane of the neuron. And you can kind of see an input spike causes a jump up of voltage, but that voltage doesn't immediately disappear like the input, right? There's some sort of transient dynamic. There's this exponential decay, and it takes a finite amount of time, right? And so that is where the leaky integrate and fire comes from. And if you keep doing this, if you keep on applying a bunch of input spikes, then you get all of these kind of membrane potentials riding or integrating, accumulating on top of itself. Finally, if that membrane potential reaches a threshold, then this neuron triggers its own downstream spike, right? Otherwise, there is no data communication going on, right? And if we can take advantage of that, then maybe we're kind of going down the right path. And a bit of a precursor here is that the mixture of experts really takes advantage. You might have heard of mixture of experts. It's this idea that a large proportion of your network is effectively switched off, and you just ask the expert, or the part of your model that that is hopefully the expert answering a particular prompt. And that is the only part of your network that is activated. And models like DeepSeek and ChatGPT take a lot of advantage of this idea. And this is just taking this to a far more granular level at an individual neuron scale, right? So I've kind of taken all of that and wrapped it up into this Python library called SNNTorch. And it's an open source library that hopefully makes it a lot easier for the community to be building more efficient language models or efficient just generic AI. It enables a set of interesting features like real-time online learning. It works effectively with PyTorch, and it's compatible with hardware that is very specifically optimized for these types of architectures. I should mention that the models that you use cannot be decoupled from the hardware that they run on, right? Now, GPUs, they don't know how to turn off individual cores, right? If I have half of my neurons active and half of them inactive, my GPU is still going to continue churning out all of the operations with zeros in them, unless I am very specifically punishing my GPU for doing that. And so this pursuit of efficient artificial intelligence is no longer just a software problem alone, right? It needs to go across the stack to hardware design as well, which is kind of convenient because I'm a chip designer by training. So there's a few cool places that are also that are using SNN Torch in certain bespoke applications. I've also put together this set of tutorials for people that do want to go and dive deeply into actually coding with these types of models. So with that being said, right, with all of that kind of preliminary-ish, non-language related motivation out of the way, I want to look at how we can combine language modeling with this kind of neurally inspired or neuromorphic approach to AI, right? And while this talk is, of course, going to focus on language, that's really not just because of the software engineering tech bro hype train. Ultimately, language models do nothing but predict the next most likely word, one at a time. And what's really mind-blowing is that in doing so, they have suddenly integrated a not so superficial understanding, or at least they appear to have this not so superficial understanding about a lot of the world. Not everything, but a lot of things, right? They're able to emulate something that looks like reasoning purely based on predicting the next most probable word. And I think that's a really fascinating thing to stress test and hopefully understand a little bit. So what can we do with this? Let's give a bit of intuition behind what modern language models are really doing. And we'll take the example, this sentence, Sundar saw Mark with binoculars, right? Sundar saw Mark with binoculars. Now, my question to you is, who has the binoculars, right? Is it Sundar? Is it Mark? Right? I see the Q&A lighting up, but this is, I'm able to give you a monologue right now and hit you with the questions for a moment. So Sundar saw Mark. Now, intuitively, I mean, linguistically, either of these guys could have the binoculars, right? It's intentionally an ambiguous sentence. But based on a bit of context, we see that Sundar saw somebody else, and therefore it's quite likely that the Google CEO is the guy with the binoculars, right? Now, in modern language models, each of these words is effectively going to be represented by a list of numbers. More specifically, sub-pieces of these words or tokens will be represented by a vector. And all of these vectors kind of come together and you build up what's known as an attention matrix. And you don't need to worry about it too much if you don't understand it. But the ultimate idea is that the model, a lot of large language models are trying to find correlations or the strength of the relationship between every word in the sentence and itself, right? So in this example, Sundar and binoculars might have a very bright red value indicating that there's a large number there. There's a tight relationship between Sundar and binoculars. And, you know, Mark and binoculars might also start lighting up a bit, not as strongly as Sundar, because this model has what I would call pretty much perfect memory, right? With every additional word, this matrix is just going to get larger and larger. And we assume in large language model processing that our GPUs have enough memory to be able to store the entire prompt, right? As a result of being able to store the entire prompt, which is something that humans are very bad at, right? We do not have perfect memory. But as a result of storing that entire prompt, by the time that I reach the end of my prompt, I still should theoretically remember everything that was said at the start of that sentence, right? So if I wanted to be a bit more quantifiable, it turns out that your memory is going to grow quadratically, right? You've got 2 dimensions in this matrix underneath, right? So it's going to grow 1 dimension, your y-axis and your x-axis. So it's going to grow to the power of 2 for every additional word that you throw into this sequence, right? Now, it's probably safe to say that your brains are not undergoing neurogenesis with every additional word that I say, right? Your brain is doing something a little bit more interesting in trying to discard information in order to make space for something a little bit more useful, right? But then one of the challenges with this if I was to just naively take this idea of what I'm saying of sequential computation that happens in the brain. And the problem is that by the time I reach the final token, I run the risk of kind of forgetting everything that I said historically, right? So by the time that Mark is exposed to my model, Mark could very well take over the importance of Sundar just purely based on its position in the sequence, right? And if I go back to that leaky integrate and fire neuron, I kind of, again, run this risk that the spike or the bit of information that corresponds to Sundar has faded over time, right? So there's got to be something a bit more dynamic. There's got to be something a little bit more interesting that can be captured by AI models that might be more brain inspired, right? And it turns out that modern LLMs just, they work really well, but they have way too much information, right? And on the other hand, spiking neural nets or these brain-inspired models, while they're incredibly efficient, thanks to all the sparsity benefits and low power advantages, there's just not enough information there, right? So how can we kind of get around this? Now, historically, with SNN Torch and a few other spiking neural network bits of research, a lot of what was out there in academia seemed to be targeting very toy problems. But my lab was really focused on and fixated on how can we scale it up? How can we do something far more fancy that really competes with what industry is putting out there? And so I think this is nearly a year and a half old, but we developed Spike GPT. A year and a half is incredibly old in deep learning time zones, right? But Spike GPT was the first spiking neural net trained to perform language generation. And it was quite nice because it actually worked, right? I mean, if I showed this to you 2 to 3 years ago, this performance sample, you'd be far more impressed. Nowadays, we kind of take this next word generation for granted. But ultimately, we were just trying to get something to work. But in doing so, we were able to get something that performed on par with similarly sized models with 30 times less operations. So it's kind of like using the constituent parts of your model more effectively rather than just blatantly scaling things up. So my self-critical question is, if this is all well, if it's so impressive, then if it's so efficient, then why isn't the world using it? And the honest answer here is that scaling hurts, right? Scaling really hurt. And so what we released was actually just a 370 million parameter model. Nowadays, we're seeing that GPT-4, 4.5, et cetera, are really kind of exceeding trillions of parameters, right? That's nearly a 10,000x difference, right? And so there is a huge disconnect. And having said that, this Spike GPT model continues to still be the largest trained spiking neural network to date, using gradient descent, using the deep learning hacks, right? So when we tried to scale from hundreds of millions to a billion parameters, the performance improvement that we get was actually very, very marginal. And my guess here is that it could just be that there was too much sparsity, right? If all of your neurons are quiet, then there's no learning signal for them to work with, right? And so we perhaps need to find some happy in between instead, right? And so what we did there to kind of address this was, I guess, in a way, try to reinvent how deep learning is done. And we've introduced this matrix multiply free language model in around June of last year. And this scales, right? We managed to show that it works at several billions of parameters on par with Llama, the other open source models that we had access to at the time. And it does so far more efficiently as well. The ways that we made it matrix multiply free, and so for a bit of context, all of modern deep learning just requires a ton of linear algebra. There's a ton of vector matrix and matrix multiplication. All of the values in those matrices need to come from memory. That's where a lot of your energy comes from. But we replaced a lot of these weights with ternary parameters. And you can kind of think, if you have -1 times a number, then that's just the negation of that number. If you have 0 times a number, you just have 0. If you have +1 times a number, that's just the original number. So from a circuit standpoint, I can get rid of the multiplication step in all of my deep learning accelerators. All I need is a cute little bit flip to represent the negation or 0 or +1. So that's convenient. We introduced this idea of learning to forget. Now, I shouldn't say introduce, right? We took inspiration from a lot of the prior literature that was coming up with interesting mechanisms to discarding information. Now, I'll talk about that a little bit more in a moment. And we were also able to achieve 13 watts at human readable throughput. So that is kind of going in that direction of being brain inspired. It is no longer strictly a spiking neural network, but we take a lot of the principles, a lot of the failures, and a lot of our learnings into this model, into building something that may very well be the future of deep learning here. If I can give you some intuition on learning to forget, because I think this is a really important idea that AI is rather lacking at the moment. Let's assume that you have one neuron and I simulate it over 3 iterative time steps, right? At t equals 0, t equals 1, t equals 2. I'm going to avoid using numbers because colors are prettier, I suppose. So let's say that I have a blue bit of information that goes into my neuron. Then we move forward one step in time. And my neuron is able to store this one blue bit of information, but now I have a yellow bit of information coming in. And unfortunately, my neuron cannot arbitrarily expand here, right? I mean, perhaps it could recruit other neurons, but if we just consider a single neuron, those two colors are going to get mixed, right? I get compression. And I'm no longer able to kind of isolate the two original sources of this dark green, murky color now, right? Now, on the other hand, I could introduce this F1, F2, something that resembles forgetting. And if I have a forget gate is what they're actually called, a forget gate of 0, and that is telling my neuron to just kind of multiply everything in here by 0, thereby forgetting everything. And if I have a 1, then it says, hey, hang on to that information for a little bit longer. And if I do the same thought experiment, then now I'm multiplying this blue by the value 0, therefore it disappears, effectively making space for what might be more important information coming in that yellow bit. And that's the thing, right? With self-attention, with transformers, with these ridiculously large language models, they don't do this, right? They just continue to expand their memory usage with every additional word that you throw at it. The brain, no, it is far, far more optimized. And by doing this, this is one of the key methods that kind of helped us perform far better, that helped us achieve competitive language modeling performance with a far more stringent memory budget and therefore power budget. So we go from this world where attention is too much information, but now spiking neural nets, or more generally just brain-inspired language models, have the correct information, right? They discard what they don't need. And I alluded to this earlier, but the honest truth is that there's only so much benefit that you can get when training these models and deploying them on GPUs, right? GPUs are incredibly good at matrix-matrix multiplication. And that's kind of thought to be one of the reasons why neural nets are so successful, because the hardware already existed to accelerate them, right? Now I'm kind of saying that, hey, why don't we take inspiration from ions and weird squidgy pink gray matter in order to accelerate our computation while making it cheaper? It is not as simple as that, right? You effectively need hardware that is tailored for all of the things that are, all of the software tricks that I'm describing, right? And so there are 3 abstractions that I want to briefly show you of the types of hardware we're working on. One of them are simply custom silicon chips. I've got a bunch of them behind me. I think they're blurred out on my camera though. We've got custom silicon chips that are specifically optimized for these types of models. And I won't go into the details, but this was something designed by one of my students, and it's kind of beautiful because it looks like a city. But all you're really seeing is a layer of silicon with a bunch of different layers printed out on top of it. And all of these little pipe-looking things are actually metal lines, right? And that's how you end up connecting trillions upon trillions of transistors together. And so this is just zoomed in at the micron scale. But what we showed initially was accelerating this model on this semi-custom FPGA hardware, where we were able to achieve 23 tokens per second at 13 watts. And for context, humans are typically reading at 5 to 15 tokens per second at 20 watts. So we kind of tick that box of human level efficiency, given the same level of performance as modern state-of-the-art, similarly sized language models. But the reality is we're hungry, right? We want to keep doing better. So how can we keep going? We linked up with Intel, who are working, outside of CPUs and new transistor technologies, they're working on a lot of exotic things, quantum computing, for example, but they've also got a team working on neuromorphic brain-inspired processors, which really just takes advantage of a lot of the high-level principles I gave. If there is no incoming data, then a lot of these cores on that low EHE processor will just be deactivated, right? It's a very event-driven processor, something that CPUs and GPUs are not so good at. So we kind of modified our software to fit the bill of this underlying brain-inspired hardware. And bear with me here. I'm going to give you some clunky graphs, but we'll see what this all means. On the x-axis, we're seeing the sequence length of the input prompt, right? If you type in more text, then your sequence length grows. If you type in less text, then your sequence length shrinks. And on the y-axis, we have throughput. That is, how many words can I generate per second? In blue, that's our model, right? And these other colors are just showing various other conventional language models that use this transformer, the classical transformer plus architecture. And it kind of shows that for a lot of sequence lengths below, say, 512 tokens, we're not actually doing any better. We're doing a little bit worse for the most part. But as you grow, as your sequence length grows, as you start processing ridiculously long PDF files, right? That's when you're no longer generating this quadratically scaling matrix, and then your throughput of our model starts to overtake. But this doesn't really show you much, because again, energy is what we are really concerned about, right? Energy is what we're concerned about. So there's this video here that factors that in. And again, on the x-axis, we have the number of joules per token, the amount of energy generated to the amount of energy expended in order to generate a single token or word if you're not familiar with tokens. And there are two different types of transformers that we're baselining against. We've got this one larger version and this slightly smaller version. The size of these circles indicates the size of the model. And so joules per token, of course, we want something smaller. We don't want much energy wasted per token generated. But then on the y-axis, we have throughput per watt. So how many, I guess, words can I generate per second given 1 watt of power, right? In that case, I would like to generate a lot of words for a single watt of power, and so higher is better. Now, if I press play, so these are what we're trying to beat here. If I zoom out, and then I'll be able to see how the matrix multiply-free language model performs in comparison to the conventional state of the art, right? So we're getting more tokens for less energy, right? We're getting much higher throughput for a single watt of power. And I have to mention that even though this model here is identically sized to this model here, this model here, hopefully you can see my cursor, is identically sized to this model here. But you might recall I mentioned that our model uses ternary parameters. That is, they're just 3 levels, -1, 0, +1. Whereas this transformer plus model is using 16 bits of values, BrainFloat 16 format. And so even though they're the same sized models with the same number of layers or neurons, the numbers used to represent those neurons is going to be significantly more expensive here. And so if I continue playing this video, you will then see these two grow to now account for how much memory they're using, right? So on a far smaller memory footprint, on a far smaller energy budget, we're able to get far higher throughput, right? And I think that is really key, but there is still so much more left to do, right? So nowadays, what we're realizing, and when I say we, I mean the entire tech bro language model community, it's that we can't just crank up the size of these models indefinitely, right? Their performance is saturated, right? One of the current preferred methods to making language models perform better now is to just kind of make them shut up for a moment and to think, right? They'll talk to themselves for a bit. They'll check if their outputs are reasonable. They'll attempt to fact check a little bit. And I think this is really cool because that is taking advantage of the brain at a very higher abstraction, right? In terms of reasoning and how do we think. But the problem is, again, we are asking over-parameterized, energy-hungry models to be run a shit ton more times, right? If you want to iterate a model, if you want a reasoning model to think longer, then you have to, I guess, get it to talk to itself more, and that is energy. So what this indicates to me is that there really is just so much left to do. I am proud of how far we've managed to push everything forward, but we need to figure out how to make reasoning a little bit more human-like, right? When faced with uncertainties, we will often spend more brain resources to figure things out. But eventually, if we do the same thing again and again, if we practice the piano enough, if we give enough talks about language models via Zoom frequently enough, it just becomes second nature. It becomes embedded within our reflexes, probably in our cerebellum. I don't know. I'm not a neuroscientist, but ultimately we don't need to think as hard. AI isn't there. We need to teach these language models how to do more with less. And again, there is so much left to do. Models like DeepSeek don't scratch the surface. We need to span the stacks. Software engineers aren't enough. We need computer scientists talking to hardware engineers to optimize beyond what GPUs are capable of, and neuroscientists to show us how the best blueprint of computation really works, right? So with that being said, none of this work would have been possible without the star students in my lab. This is not a one-man effort by any means. There's always a team backing this kind of thing. And with that being said, I think that's more or less all I've got to say.
Thank you. Thank you, Jason. Very interesting. Let's see first the audience, if they have any question. Looks like it's mostly conversation with Christina. Anyway, so then let's move on. So my question, okay, so two things. So first of all, this idea of the spiky neural networks, I mean, the scientific study, the model, the formula, it's pretty old, right? 1952?
Oh, the leaky integrate and fire neuron, that comes from 1908-ish.
Wow. So we have known this this model of how the neurons work for a long time. And so basically the artificial neural networks we have today are really a simplification that started in the 40s. And in a sense, do you agree that they have moved away from biological intelligence in a sense?
Yeah, big time.
Yeah, it just works. I mean, moving away from biological human intelligence actually works. It recognizes speech, it recognizes images, and it even generates text.
Yeah.
In fluent English, which is a philosophical discussion there.
Yeah. So my take is that we shouldn't copy the brain for the sake of it, right? There are certain things to the brain that don't necessarily make sense on silicon, right? Should I imbue my transistors with sodium, calcium, potassium channels? Probably not, right? Probably not, because it's a difficult thing to engineer onto silicon. Should I force myself to only strictly use spikes? Probably not, because spikes, as I think was brought up in one of the comments by David, spikes may be seen as a solution to long-range distance communication challenges, and the specific mechanism by which spikes are generated is a result of the constraints, the physical constraints of the brain, right? Silicon has a very different set of constraints. So philosophically, at a very, very high level, I do not think we should copy the brain. I think what makes sense is, at a somewhat arm's length, if you will, understand what it is about the brain that gives rise to energy efficiency. And I think there are a lot of principles across predictive coding, I guess local learning rules, Hebbian plasticity, a lot of these things that, I mean, came about from a very different community, that were discovered by a community that are not engineers, that are computer scientists, that are not computer scientists or chip designers, but can provide a lot of benefit to those same communities, right? Right now, they're all relying on gradient descent, backpropagation, which is a disgusting amount of weight movement, of a lot of data movement. Can we do better? Can we find how the brain is adapting in a way that doesn't require so much data movement? I think we really need to pick and choose the mechanisms that make sense. I've kind of given an intuition on what I personally think, a small snapshot of what I think makes sense, but there are a lot of things that I don't think make sense as well.
But no, philosophically speaking, besides the fact that you have a sustainable solution that the traditional neural networks don't have yet. But besides that, philosophically speaking, it is interesting to realize the kind of complexity we need if we really want to build machines based on biological human intelligence. One thing that is still missing, even if I give you neuromorphic hardware and you can implement your model, um, you still assume that all neurons are the same, for example. We have 86 billion neurons, and they're all different, right? They're all come in different shapes and size, not to mention function.
Yeah.
So if we wanted, again, philosophically speaking, if we wanted to really build a machine that does what the neurons do in our brain, the complexity is just mind-boggling, right?
If we want a one-to-one kind of translation, then yes, I would say that it doesn't make sense to do that given the silicon that we've got. What could potentially make sense is, hey, if we know that silicon is, it can be manufactured in an incredibly modular way where even though the most optimized thing is an architecture where there is a painful amount of repetition, then how can we do better with that? It could be that a particular set of neurons, of artificial computational neurons, may just learn to emulate the function of one specific cell type that is, doing its own very complex behavior. And then another set of neurons that again, are artificial and on their own are very simplistic, may be giving rise to another particular neuron type. So I think that the fact that there is a huge degree of modularity in silicon doesn't necessarily preclude you from taking inspiration from the rich heterogeneity of the brain, right? I'm just spitballing ideas here.
Oh, it's good. Somebody is asking what happened with IBM True North. I make the question a little bigger. What's happening with neuromorphic computing? Why big companies are not investing in this area? I think I know the answer, but I want to hear your opinion.
So, I mean, I would say that companies are investing in neuromorphic computing. A lot of companies are investing in neuromorphic computing. It might not necessarily come with the branding of neuromorphic computing, but ultimately, there are so many startups and big tech companies that are drawing upon a lot of the work that we have done or that has been done in the past 30 years or so. But why isn't there a sudden phase shift in technology from regular CPUs or GPUs, von Neumann architectures, over to something that is completely different? To address that, I would say that it's expensive, right? If I told you that, if I told you that I suddenly discovered a way to build railway tracks that are a little bit more efficient, that waste a little bit more energy by changing their distance from one another by 3 inches, you would say that's great. What a shame we didn't do that 50 years ago. It's too expensive to tear out every railway track and rebuild them, right? And I think that that's kind of similar with modern computing, right? A lot of software has been hyper optimized for x86 architectures or whatever the dominant trend of architecture is. And changing that fundamentally requires a good justification, a good cost justification to do so. And so a 2x benefit, a 5x benefit doesn't warrant people throwing $100 million at the problem. You need something that is really compelling, that really exceeds the trajectory of Moore's law. That is why I really think that neuromorphic computing hasn't overtaken the mainstream. Having said that, though, there are pieces of neuromorphic computing that we are observing, right? There are certain things in gradient approximations that are coming up in the LLMs. There are things like continual online learning. Google have released this associative memory mechanism with their latest state-of-the-art language model. Liquidity, a startup out of MIT, they're working on these hybrid models that take part inspiration from transformers, partly from these recurrent dynamics that stemmed from the neuromorphic community in 2018. So all of this does exist in the mainstream. It's just kind of been rebranded a little bit. And that is okay.
Excellent. Okay, do you feel that the current landscape of hardware software is ideal? for the kind of architecture you're going for in optimizing for neural networks?
Yeah, this is a really good question. I'm just going to kind of read the first sentence for now in the interest of giving a quick answer. We are working on things across the stack, right? We did, I mean, there's what, something like 10 PhDs in my students, and some of them are working on things that are higher risk, that do really require a restructure in how hardware is approached. Some are working on things that, target what industry are looking for a little bit more, something with more quarterly benefits that are already adapted for hardware that is pre-existing. And we do both because the reality is that will neuromorphic computing take the center stage? I don't know. I think that it's a really good thing to invest in. I think that it has a lot of promise. But if I was to tell you that with 100% certainty that one technology is going to dominate the others, that would be a lie, right? So we kind of hedge our bets across a few different things and hope that one of them pan out.
You said you're working on your own custom chips, correct? Yeah. How those are different from the ones you can buy?
Oh, so I mean, let's compare them to GPUs and modern accelerators. To start with, modern GPUs, accelerators, GPUs follow the SIMT architecture where they take a ton of data, allocate a bunch of threads, and they just execute all the cores that they need. Always doing something. They have this static power dissipation. My H100 in my desktop computer has a static power dissipation of, say, 200 and something watts, even when I'm not kind of utilizing it. All I've done is turn my computer on. That could be things, even though I'm not processing anything. And now that could be because there's a clock distributed across this chip. The neuromorphic chips that we've got, they are effectively clock-free, or some of the chips that we have are not clock-free because that is very hard to design, but we just know when to switch things off a little bit more effectively. They are generally less general purpose, right? GPUs are great for graphics, but they are also very general purpose. They can do a lot of things. They can do graphics, games, AI, anything parallel. GPUs are a damn good solution for that. Our architectures are considerably different, right? We do not want to be super general. A degree of generality is good, but we don't want to solve everything in one hit, right? GPUs are good for that. The MATML free language model, for example, that uses ternary parameters. GPUs, you can go down to floating point 4, a 4-bit kind of format, but then you have a whole heap of redundancy, right? So it's all about having the software that has a set of constraints that theoretically give rise to benefits. Those benefits are theoretical because the GPUs can't take advantage of those low numerical formats or specific ways to use cache. As a programmer, I might not be able to access that level of detail that I might need in a GPU through CUDA kernels, but my hardware does let me get that access, right? A lot of these nuanced little design decisions that kind of switch off things when they're not needed. I think that is probably the key thing amongst a bunch of other things.
Yeah, I think it's good. I think it's good. This was an excellent introduction to this whole field that is not as publicized as generative AI.
Yeah.
So great.